So today we cover lecture number 5, which is one of the components of concrete mineral admixtures. Okay. So in concrete, the major component, including, of course, cement, okay, and together with water, we have cement paste, and we have hydration goes on between cement and water, and we discussed the hydration process. Okay. And besides that, we have two different types of aggregate, okay, including sand and also coarse aggregate. Okay. And we also have some admixtures. Admixtures is not in every concrete, but in most of the concrete, we have some type of admixtures, including two types. One is called mineral admixtures, which we will discuss today. The other is called chemical admixtures, which will be discussed next time, I think. Okay. Right. So here shows the history of mineral admixtures. More than 2,000 years ago, the famous Pantheon actually was built with one of the mineral admixtures, which is volcanic ash. Okay. By definition, mineral admixtures is to replace part of cement. So we also call that supplementary cementing materials, or supplementary cementitious materials. Okay, we also call that binders. Okay, mineral admixtures is a material that, when used together with Portland cement, contribute to the property of hardened concrete with hydraulic or pozzolanic activities. Sometimes both hydraulic and pozzolanic activities. Okay, so hydraulic properties means the material will react with water and we have hydration product. Pozzolanic properties means the materials will react with some type of alkali, such as calcium hydroxide, okay, and together with water, and we have hydration product such as CSH. Okay, so this is pozzolanic reaction we discussed last week. Depending on the chemical composition, some of the mineral admixtures has only pozzolanic property, and some of them has both hydraulic and pozzolanic properties. And here shows some of the major SCMs, okay, supplementary cementitious materials. Okay. So including from left to right, class C flash, okay, and also class F flash, okay, which is the first from here. The difference between class C and class F flash is the percentage of calcium oxide, CaO. For class C flash, the calcium oxide percentage is more than 10%. Less than 10% calcium oxide, we call that class F flash. Okay. We also have metakaolin, okay, also called calcium clay. Okay. So this is a type of natural minerals, okay, the whitish color powder. The third one is called silica film. Silica film is one type of industry byproduct. We'll discuss that in more details in a moment. Okay. And then class F flash. The white color powder here is called slag. Slag is a byproduct from steel manufacturing process. Okay. We also have calcium shell. Okay. calcium shell is one type of natural minerals. Okay. So this is some example of supplementary cementitious materials. All right. So here's a couple of more definitions. Pozzolans, I think we discussed pozzolans last time. It is a siliceous, sometimes also have aluminum in it. So siliceous materials that it is in finely divided form and together with moisture. Okay. It will chemically react with calcium hydroxide. Okay. Sometimes other type of hydroxide will also be okay. Okay. And it will form CSH. Okay. Depending on the source of pozzolans, we could have natural pozzolans, okay, such as calcium clay, metakaolin, or red cast ash. Okay. Volcanic ash is the ancient Roman engineering used, or calcium shell. Right. Before we go into the details of SCMs, let's look at ecological advantage of SCMs. Okay. So power plant use coal ash as a fuel, and then we have flash from the coal burning power plant. Okay. The manufacturing process of cast iron or silicon metal or some other alloys will produce silica fume, slag. Silica fume or slag. Okay. So these are the waste product from the industries. Every year generate a million tons of them. Okay. And most of the time, we dumping this byproduct into landfills or even streams. So that will generate a big concern because they may pollute the environment. We could use this type of materials in two major applications. We could either dispose them as aggregate, use them as a sand or coarse aggregate. Okay. But this is a low value use because aggregate is much cheaper. We use these SCMs as aggregate. So we do not fully use the potential of these materials. Okay. Or we could use them to replace cement. So we use them as mineral admixtures. But the quality control should be well designed because these materials, such as flash or slag, are industry byproduct. So the quality control could be an issue. Okay. So whenever a pozzolanic or cementitious byproduct can be used as a partial replacement for Portland cement, it will represent significant energy and cost savings. So that's the reason why we want to use more these type of materials to replace cement. Okay. So here in Civil Engineering Department of UH, so we have several projects trying to use more flash or more slag, sometimes more other type of waste such as red mud to replace cement. I will introduce more of this interesting project in the future lectures. And here shows the pozzolanic reaction, which is coming from previous classes. Okay. So calcium C3S or C2S together with water, and we generate CSH plus calcium hydroxide. Okay. And we know CS is stronger and also insoluble compared with calcium hydroxide, which is weaker. So Pozzolanic reaction is the pozzolans, which mostly has silica oxide, sometimes aluminum oxide. So plus calcium hydroxide, which is coming from hydration of C3S or C2S, and plus water, and we have CSH formed again. Okay, so this reaction is called pozzolanic reaction. It will transfer the weaker calcium hydroxide into stronger CSH. Okay. And also because CSH is insoluble to water and calcium hydroxide is soluble to water. So that will increase the durability of concrete. Another reason for why pozzolanic reaction is good is because the volume will be increased. So the volume of CSH is more than the volume of pozzolans plus calcium hydroxide. So the volume of the solid will also be increased. So that will reduce the porosity as well as the permeability of concrete will also be reduced. Okay, and because permeability controls the durability of concrete, so concrete durability will increase. Durability will be increased. Another point about pozzolanic reaction is it needs continuous moisture curing. We need long exposure to water for pozzolanic reaction to continue. It takes months or even years for pozzolanic reaction to finish. Okay. So this is different from hydration of Portland cement. For Portland cement, after 28 days, first month, more than 90% of the reaction will finish. Okay. But pozzolanic reaction will take a longer time. Another thing about pozzolanic reaction is it is temperature sensitive. Increase the temperature, the reaction will be faster. Reduce temperature, reaction will be much slower. So if the temperature is not very high, it may take months or even years for pozzolanic reaction to finish. But under high temperature, such as steam curing, the reaction will be much faster. So it stops. So we are sharing stopped. Okay. All right. Okay. So here shows the specs for fly ash. Okay. So fly ash is the byproduct of coal burning process. For example, coal burning power plant. Every year in the world, we generate, this is old value, old data, 250 million tons every year in the world. I think right now it's more than 500 million tons every year. The cost of fly ash is much lower compared to cement, depending on the source. Okay, for example, for cities which have coal burning power plant, the price of fly ash will be much lower compared with areas which does not have a coal burning power plant. Okay. But typically, the cost of fly ash is much lower compared to cement. And depending on the percentage of calcium oxide, we could have class F fly ash. So class F fly ash has calcium percentage less than 10% calcium oxide. Okay. So class F fly ash has pozzonatic properties only, because mostly the chemicals is silica or aluminum. If the calcium oxide percentage is more than 10%, we call that class C flash. Okay, so for class C flash, it has both pozzolanic properties and cementitious properties because the calcium percentage is higher. Okay, which means for class C flash, it may form CSH by itself. Okay, so this is the difference between class F and class C flash. So here, instead of Hawaii, we have flash coming from a local power plant, which is called AES. AES power plant, it is located in Kapolei area. Okay. So every year in Hawaii, we have 300,000 tons of flash every year. Okay. But most of this flash cannot be used because the sulfate content in this flash is too high. So we cannot use that in normal Portland cement concrete because it may cause potential sulfate attack. However, one of the projects we performed here at UH, we try to use a local AES flash without any cement. Okay. So the $10 result is very good. We could use up to 100% of local flash with no Portland cement. And the strength of the concrete is very high. Okay. So again, this is an interesting project and we will introduce that to you in future lectures. So this is SEM picture of flash particles. The size of normal flash is similar to Portland cement. It's around 10 to 15 micrometer in diameter. We also can see the speckle shape of flash particles. Okay. Some of the particles are hollow inside. Okay. So because the speckle shape of flash particles, when we introduce flash to concrete, it may facilitate the mixing of concrete. So the requirement for water, for mixing water is lower when we introduce flash into concrete. As we can see from here, the water requirement is reduced for different type of flash. We call that effect ball bearing effect because the speckle shape of flash it will act as a ball bearing, so we can mix the concrete easier, reduce the requirement for mixing water. Okay. So this is one of the benefits of using flash in concrete. Okay, the second SEM is called silica film. Silica film is a byproduct of silicon, ferrosilicon, or other silicon-containing alloy. Okay. The cost of silica film is very expensive. It's around 10 times the cost of cement. Okay. So when we use silica film in concrete, the purpose is not to reduce the cost. It is to enhance the performance of concrete. Okay. So actually for high strength concrete, normally we use at least 5% of silica film because silica film can greatly enhance the strength of concrete due to many reasons. Okay. One of the reasons is called feeder effect, okay, because silica film is very small, so around 1% the size of cement. And because of that, it can increase the so-called packing density of concrete. So let's say this is cement particles. Okay. And we mix cement particles with water, and we ignore aggregate here. But when we introduce silica film, which is much smaller than cement, okay, the silica film can pack into the spaces between cement particles. So we increase the so-called packing density. So basically means in a unit volume, we can put more solid into the system. So more solid, less porous. Okay? So the strength of concrete with silica film will be higher. Okay. Again, silica film is a byproduct of silicon metals or other type of alloy. Silica film has spherical shape, very small particle size, and also very reactive. Okay, we call that non-crystalline silica. So very, very reactive. Okay. So actually, more than 90% of the silica film can be reacted with potent cement. And here is SEM picture of normal potent cement. So the size around 10 to 15 micrometer. Okay. So normal flash, similar to the size of cement. Okay. Also spherical shape. For silica film, the shape is also spherical, but the size is much, much smaller. Okay. If we zoom in, we see it's spherical shape, but the size is much smaller. For ultrafine flash, we have smaller size, but it is still much larger compared with silica film. Okay. Before we continue, we said one of the reasons silica film can enhance the strength of concrete is we call that a feeder effect. Okay. Because the size of silica film is very small. Another reason, it is very reactive. Okay. And also, silica film is pozzolanic materials. Okay, so the pozzolanic property of silica film will also contribute to higher strength of concrete. Okay. So the next one, I believe the third one is called slag. Okay. The full name for slag is called granulated iron blast furnace slag. Slag is a byproduct from metal production, mostly iron. Okay. Slag has much higher percentage of calcium oxide compared with flash and silica film. And because of that, slag has hydraulic properties, which means it can form CSH by itself, but it needs some kind of activation by alkalis, such as calcium hydroxide from potassium hydration. Okay. So again, it has hydraulic property due to high calcium oxide percentage. Okay. So slag has different grade from grade 80 to grade 120. Okay. it is depending on a so-called activity index. Okay. So activity index is defined as a ratio of two types of samples. So one is a mortar sample with 50% of slag and 50% of cement. Okay, so this is 2080 strands of the sample with 50% of slag and 50% of cement versus over the strands at 28 for 100% of cement. Okay, so the water cement ratio of these two types of sample is the same. So the higher ratio of sample with 50% of slag over the control sample, which is 100% of cement, the higher the grade. Okay, so for example, grade 120 means the activation index is equal to 1.2 or 120%. Okay. And here shows the physical properties of some of the pozzolans. As you can see for flash, okay, silica film, rest husk ash is the ash coming from burning rest husk, okay, and also calcium clay is not another natural source of SCM. We can see the particle size for silica film is very small. The surface areas of some of these materials are very high. We can see for silica film is much higher compared to Portland cement. Okay. So that means the reaction speed of silica film is also very high. The higher the surface area, we have more contact or more hydration between water and these materials. So we have faster hydration. For rice husk ash, because it is a cellular shape, so we have a hollow shape for rice husk ash, the surface area is even higher. And here also specific gravity for these materials. For flash is a little bit lower compared to Portland cement, which is around 3.1, 3.2. Okay. Silica film is also around 2 point something. And this slide shows us the chemical analysis of typical SCMs. Okay. All right, so focus on silica oxide, aluminum oxide, and calcium oxide. Okay. So again, some of them has only pozzolanic properties, such as class F flash, okay. Silica film, okay. Calcium clay, calcium shell, and metakaolin. Some of them has both pozzolanic properties and hydraulic properties, or we call that cementitious properties, which means they can form CSH by itself. So class C flash, which has more than 10% of calcium oxide, and also slag, which has even higher percentage of calcium oxide, in this example around 40%. So due to calcium oxide percentage is higher in slag and class C flash, they have hydraulic properties. Again, they can form CSH by themselves. Okay, and here shows the difference between glassy versus crystalline component. Okay, we don't need to dig too deep into this concept. Just remember, when we have more glassy fractions, that means this material is more reactive. When we have more crystalline fractions, more likely the material is less reactive. Okay, that tells us, here shows the chemical composition of the materials. Tells us the percentage of silica. For example, class F flash, in this sample, we have 52% of silica oxide. But that does not mean all these 52% of silica oxide is reactive. So depending on how much this 52% is reactive or glassy, or how much of these are crystalline or less reactive. So the actual reactivity of these materials could be very different. Okay. For the typical amount of SEM in concrete, this is by mass of cementitious materials. So for class C flash, we can use, here says up to 40%. Okay. For class F flash, we can use around 20%. This is kind of old number. Okay, so in nowadays, we could use more than 50% possible. Okay. And for some extreme case, like the research project we did here, that project is called geopolymer concrete. Geopolymer concrete, or another name is called alkali activated concrete. For this concrete, we can use up to 100% of flash or slag. Okay. Again, this is just a typical number. For slag, because slag has both hydraulic and cementitious properties, we can use higher percentage. Okay. For silica fume, normally 5%, 10%, sometimes 15% or even higher is possible. But when we introduce silica fume into the concrete, it may tend to reduce the workability, which may make the concrete very sticky and very hard to mix for the concrete. Okay. In the first lab session, which will be maybe next week or the week after, we're gonna mix different type of SEMs, such as flash, slag, and silica fume, together with water and cement. And we compare how easy the mix can be made. Okay. For calcium clay, we can use up to 35%. And the calcium shell, we can use up to 35%. And then let's look at how these SEMs can affecting both fresh properties and also hardened property of concrete. Okay. It may control the bleeding. Bleeding actually is a separation between water and cement paste. Okay. For example, if the water cement ratio is too high, some of the water may separate from cement, and we can see a water layer on top of the concrete, and we call that bleeding. Okay. I introduce flash or slag or silica fume in concrete, we may reduce the bleeding of concrete. Okay. If we also refine the grain, okay, because these materials can transfer the larger calcium hydroxide crystal into CSH. Okay. Enhance the strength, will also increase the durability of concrete. It will also reduce the porosity, okay? Reduce the porosity and increase the durability. Okay. Workability can also be improved. Workability is defined as how much energy we need to introduce in concrete to fully compact it. Okay, so by introduce flash, it will improve the workability of concrete, make the concrete easier to mix. Okay. It will also enhance cohesiveness together with workability of concrete. Consistency may also be increased. Okay. But here we'll give some definition for these words. Cohesiveness is defined as the tendency for concrete to not bleed or not segregate. Okay. So not bleed or segregate. So the segregation means the separation between cement paste and sand and coarse aggregate. We'll talk about bleeding and segregation in more details in future lectures. Workability is defined as the energy needs to compact concrete. So we can say the concrete has good workability, which means the energy need to compact concrete is less. Consistency, on the other hand, is defined as how easy the concrete to flow. So the three words, cohesiveness, workability, and consistency, is pretty much similar, but not exactly the same.
Could you repeat what you said for workability again?
The workability is defined as how much energy is needed to fully compact the concrete. You know, when we introduce the concrete into the form, most of the time you need to compact the concrete. You either use steel rod or vibrator. Okay. A concrete with good workability means it does not need much compaction for the concrete. Okay, so all mineral admixtures tend to increase cohesiveness, consistency, and workability of concrete, but not to the same extent. Okay. So this table summarizes how different types of SCMs affect fresh property of concrete. Okay, so focus on water requirement, which is defined as how much water is needed for the concrete to be mixable. Workability, again, how much energy is needed to fully compact concrete. Segregation and bleeding, okay. Heat of hydration, and also setting time. Okay. You can see, for example, flash and slag, it will reduce the water requirement, reduce the heat of hydration, and increase the setting time. On the other hand, silica film will increase the water requirement because silica film is very small, has very high surface area, so that will increase the water requirement to achieve a certain workability. However, we could use a type of chemical admixtures, which is called super plasticizer. We'll discuss that in next lecture to compensate this effect. Okay. So this figure shows us long-term strength of concrete with flash and without flash. So the blue square shows us the data for concrete without flash. As you can see, after around a month or so, the curve will be flat, not too much increase in strength after 1 or 2 months for concrete without flash. For concrete with flash, which is the red class, the strength will keep going up after months or even years. Okay, so this is again because pozzolanic reaction is a slow reaction. It needs continuous moisture curing over a long period of time. And here shows the strength development of concrete under cold weather. Okay. So we have a control, which is 100% of cement. With the other three, which is flash, around 20% of flash. Okay. Compared with the control mix, concrete with flash will have a lower early age strength. So you can see the early age strength up to first month, 28 days, is lower for concrete with flash. But the strength will catch up and more than a control mix after the first 28 days.
For fly ash A, I'm confused about the difference of that than like C or F.
Yeah, this is the details you don't really need to care about. I can tell you. For the first one, the green one is flash with 20% replacing cement. Okay, and for the second one, the purple one is 10% of cement, and so the flash will replace 10% of cement and 10% of the sand. And for the third one, is adding 20% of flash and mass of cement. It's just a little bit of difference, but you can just remember we add around 20% of flash into the concrete. Okay. Thank you for your question. Here shows silica film. Silica film is different from flash because at early age, concrete with silica film will not reduce strength. Okay. The strength will be similar compared with the control mix for concrete with silica film. This is again because silica film is very reactive. Okay. High surface area. Okay. And also the particle size is small. Okay. And silica film, the particles is very reactive in nature. So that will compensate the pozzolanic reaction, which is the slow reaction. So concrete with silica film, the strength will not go down at early age. The strength at a later age will be much higher compared with the control mix, as we can see here. Okay. Also because this reason, silica film is very reactive. Silica film also has the failure effect, which we just discussed earlier today. Okay. So that's the reason for high strength concrete. Typically, we use around 10 to 15% of silica film for high strength concrete. Then let's look at durability. Okay, so durability to thermal cracking. When concrete crack due to high temperature, it will reduce durability because when concrete cracks, the harmful chemicals will get into the concrete to more damage easily. Okay, but because pozzolanic reaction is a slow reaction, as a result, the temperature rise in concrete when we introduce flash or slag will be lower. So that will reduce cracking due to high temperature. The total heat of hydration will also be lower because pozzolanic reaction is a slow reaction. Actually, we can think pozzolanic reaction will generate only about half of the heat compared with Portland cement. The permeability of concrete with pozzolanic materials will also be lower because of the reason we just discussed. And because permeability is lower, it will reduce the potential for chemical attacks such as alkali-silicate reaction, or called alkali-algae reaction, which will be discussed in future lectures, and also chemical attacks by acid or sulfate. Okay. The reason is because it will reduce the pore size, reduce the porosity. Okay, we call that pore refinement due to pozzolanic reaction. For silica film, the pore size and porosity can be further reduced due to the small particle size. Okay. So mineral admixtures can improve the resistance of concrete to acidic water, sulfate attack, seawater. Inside the seawater, we have a lot of chloride, which could potentially cause corrosion of reinforced concrete. Okay. So by adding mineral admixtures, we can improve the concrete durability due to these attacks. Okay. Again, pozzolanic reaction can reduce permeability, okay? And also reduce the amount of calcium hydroxide. It transfers the calcium hydroxide into stronger and more durable CSH. Right. So this table summarizes how SEMs affect hardening property of concrete. Okay, the strengths, mostly flash and slag will reduce early age strengths, but increase the final strengths. That's why we see it depends on what time the strength is. For silica film, both early age and the final strengths will be higher. Okay. Permeability, most of them will reduce permeability, so increase the resistance to alkali-silicate reaction, chemical reaction resistance will also be increased. Okay, so mostly by adding SEMs, the hardening property of concrete will be enhanced in general. Okay, so in summary, by adding SEMs, will transfer the calcium hydroxide into CSH. So that's the major benefit. It will also densify the matrix, the concrete. So by densifying the concrete, it will increase the durability by reduce the permeability. Okay. It will also reduce the thermal cracking because it can reduce the hydration heat. In general, it will improve the workability and cohesiveness, consistency, but for silica film, it may somehow reduce the workability. We can compensate that with chemical admixtures such as superplasizing. We'll discuss that next week. Okay. It will also reduce the bleeding and segregation, okay, and increase the final strength. For early age strength, it may not increase. For early age, it may reduce. For flash and slag. Okay. All right, so this is some of the questions for you to think about it after the class. And we also upload the first homework to Laurima. Okay, the due date is 2 weeks from now, I think.